Wonderful. Okay, cool. We can see the slides. So, yeah, today we have a two-part topical meeting as part of Diana HEP series. The first talk for the first half an hour is going to be on Swordfish, and then followed at 6 o'clock here at 7 in half an hour on Apache Arrow. So, let's begin. Okay, whenever you're ready.
Okay, thanks very much for having us. If you can't hear me, just complain if the connection is not good. Yeah, so I will talk about Swordfish, which is a package that we developed during the last couple of months, Python package, with a basic goal of doing forecasting for generic Poisson processes. So we come from the direction of astroparticle physics, indirect dark matter searches, direct dark matter searches, and yeah, kind of the reason to actually develop the tool was to streamline much of the things that we were doing in a repetitive way over and over again. So I will start with a brief motivation for what we are doing, and then spend a lot of time on actually explaining a few approximation schemes that we developed to apply Fisher forecasting also to Poisson processes in the deep Poissonian regime, which was one of the criteria that we had, because especially for direct dark matter searches, but also dark matter searches, like at very high energies, usually one is in the signal limited regime, or often at least. And I will also show a bit how the interface to the code actually works. And then finally also talk about some concept that we introduced, and that we were able to introduce because everything is basically using Fisher forecasting, so easy to handle analytically, which we call information flux. That's kind of a generalization of a signal-to-noise ratio, but taking into account background systematics and uncertainties. And you will see a bit later how this might be useful. And the idea was here basically to have a handle for experimental design, or in the context of astroparticle physics, like observation strategy planning. Okay, so the motivation was that lots of literally everything I have to do usually on a day-to-day basis are Poisson processes. If one talks about astronomy, gamma ray observations, the Poisson processes, obviously also in collider experiments or direct dark matter searches, yeah, Poisson processes. And what we were missing, or what we wanted, was just a forecasting tool that we could throw at all problems, irrespectively of the details, and just get right answers. Especially something that, for our purposes, is in principle applicable from radio frequencies all the way up to gamma rays. And yeah, the idea was to have a tool specialized for Poisson processes, exploits Fisher information techniques as much as possible, and streamlines most of the typical tasks that one actually has. And you will see in a minute what this means. So the statistical model that Swordfish is built around is just shown here. So that's maximum log likelihoods, which has a Poisson part, which is completely arbitrary. It use just the expected number of events, and D, the number of observed events. And then there's also a part that encodes the prior on background uncertainties. You see that mu is defined simply as the sum of signal plus background plus whatever background variations you have times some exposure. And this delta B, the background variations, can vary as it is described by this covariance matrix, which is, as I said, completely free. And with this, one can also one can capture basically everything that is interesting, as long as the background variations are not too large. So in astronomy, this can happen. Things are uncertain by orders of magnitude. This runs into problems, but if it's tens of percent or whatever, this typically works. And then the signal itself can be, in principle, arbitrary function of parameters, although then the details depend, or what exactly can be used in Swordfish depends on the specific functions one is interested in. Okay, so that's kind of a brief overview of some of the things that we wanted to implement or already implemented. So the basic idea is to map this Poisson point process plus a Gaussian random field for the background uncertainties. First, just on the Fisher information matrix, calculate this thing, and then based on this matrix, one can either do calculate the exclusion limits or discovery reach, and for this we used what we called equivalent counts. I will talk about this a bit. Then one can interpret the Fisher information matrix as a metric in the model parameter space. And in this case, one can do stuff related to information geometry. One important thing is to calculate expected confidence contours for model parameter reconstruction. These are just equally geodesic distance contours in this case. But one could, in principle, also do a bunch of other things, like looking at volumina of parameter spaces or estimating trifactors. And then we introduced something that we called equivalent shape method, which is basically also a method for estimating the model discrimination power of experiments, but for more complicated parameter spaces. And then, as I mentioned, information flux, which is, yeah, as you can see here, basically defined as the derivative of the Fisher information with respect to exposure. But I will say a bit more about this later. So for our problem, the Fisher matrix basically is defined as it's shown there. So it's the second derivative, in our case, of the log maximum likelihood. So the likelihood is here maximized with respect to the background uncertainties. We profile them away. And then it turns out that the Fisher matrix actually has a very simple form ultimately. It's just yeah, as shown here. So the signal derived with respect to the model parameters, and in the middle you have the covariance matrix plus the shot noise part. So the D is just the sum of background plus signal divided by the exposure plus the covariance matrix for the background uncertainties. And that's a very simple form. One can just, even for very large problems, solve this numerically, either by matrix inversion or by solving a linear system. So that's usually easier to handle. There was something. Was this? This was just your computer. Okay. Example. Good. So in order to show you something in the context of a specific example, just take what we show there. So we have two background components, red and green are signal components, potential signal components, plus some realization of the background uncertainties, this Gaussian random field. You see on the right, like the covariance matrix that we use in the example illustrated. One could use anything here. And for the backgrounds, we assume that one of the components is completely fixed. The other might be uncertain by 10% or so. And then what one can do is to simply instantiate a Swordfish instance by providing information about these backgrounds. So about the shape of the background fields as well as their uncertainty. This is T. The shape is just defined by B1 and B2. And then exposure and covariance matrix are also parameters. And everything else of this object. So the background is fixed, or, yeah, defined at the beginning, and then one can look at various signals afterwards. And looking at covariance matrices is...
Can I ask a quick question?
Yeah, other questions?
So at this point, the way that you provide this is just purely in terms of arrays. I mean, you have a function there, but the Swordfish is not knowing doesn't know the function itself. You just provide this arrays.
Yeah, exactly. So it just takes arrays with arbitrary shape. And the covariance matrix applies to the flattened version of these arrays. Yeah. But actually, the covariance matrix could also be a linear operator. So in some cases, if it's very huge, then that's better. So it doesn't have to be dense.
Okay. But I mean, so in terms of like taking derivatives with respect to S and the model parameters and things?
This comes a bit later. So at this point, this is just defining the backgrounds. And for the backgrounds, we assume that uncertainties are, these components B1 and B2 are just summed, and their uncertainties are specified with T, so that's just the normalization. And then if one has more complicated variations, in principle, this can go onto the covariance matrix.
Okay, but the S dependence on theta, that part of it?
S will come now, next.
Okay, sorry.
Good, so just a few examples. So in the simple case where S is a sum, so additive model like shown here, one can calculate then easily the Fisher matrix or the covariance matrix by just providing like a list of these arrays defining different signal components. So that's more or less trivial, but that doesn't, so the specific, this assumes the specific form of the signal, so this additive form. And also in the subsequent slides, I will first assume that the signal basically has a fixed shape and maybe several components that are, however, also fixed. So the generalization to arbitrary shapes comes a bit later. The point why we make this distinction is if one looks for projected upper limits or sensitivities, then usually the assumption is that the signal shape is fixed. And under this assumption, one can make play a few tricks or use a few approximations that wouldn't work for the more general case. So exactly, this brings me to the equivalent counts method. So if everything would be Gaussian and nice behaved, large number of counts, then usually just using the covariance matrices is enough to say everything about projected upper limits and discovery reaches. But this is usually not the case if one has very low counts. So what we tried to do, and it seems to work well, is to extend the Fisher forecasting framework to the deeply Poissonian regime by kind of mapping the entire problem onto a single bin Poisson process. So imagine now the situation where we have a single signal component, only the normalization is uncertain. Then we can define this sigma square, which is just the variance of the signal. And we can also define this sigma square, which corresponds to signal goes to 0. Basically, that's the variance of the signal if the signal wouldn't contribute to the background noise. And what one can then do is to define this equivalent number of signal events and background events in this somewhat abstract way that you see there. Basically, this is a mapping of the entire problem onto just two numbers. And this process is defined such that if one applies it, if one throws it on a single bin Poisson problem with fixed background, you just get the numbers back that you put in, so number of background events and the number of signal events. In the Gaussian regime, this just becomes signal to noise ratio. So S squared divided by B plus S becomes the Fisher information matrix. So this behaves then also as expected. And in between the deep Poissonian regime and the Gaussian regime, it works reasonably well. But what this allows basically is to replace this profile log likelihood ratio simply with a Poisson ratio of signal bins. And for this, one actually knows how to calculate projected upper limits and the discovery reaches. And so before I show results for that, just to illustrate a bit how these effective signal and background events work. So basically, if I go back, If I go back, if you look at this green line, the signal line, what equivalent signal events refer to is just the number of signal events inside the signal or the part of the signal that is basically statistically relevant. And the effective background events correspond, roughly speaking, to the number of background events in the signal region. So it's kind of an abstract definition for a very simple concept. And so if one looks at the specific example, then you see here the counts, the effective signal counts and background counts divided by the exposure, so counts per exposure, because that's like a trivial scaling. And on the left side, you basically see the number of equivalent signal events is slightly smaller than the total signal events, and the number of equivalent background events is much smaller than the total number of background events, simply because only the ones in the signal region count. And as soon as one increases the exposure and enters the regime where things become affected by background systematics, these numbers diverge. And then at some point one hits the systematic saturated regime, and they just explode. And this simply corresponds, in this language, basically, in the systematics dominated regime, what happens is that the background events grow so fast that they account for or overcompensate, or exactly compensate growth in the signal events. Okay, so in practice, one can use this simply to calculate the discovery reach then by solving this Poisson likelihood ratio as shown above. So that's what one also would be roughly doing if one had a single bin process. And this turns out to be work well as long as the number of equivalent background events is above 10 to minus 3 or whatever, if one is interested in up to 5 sigma detections. Then for expected upper limit, the story is much more complicated because obviously there are many methods to define upper limits. Usually there are compromise between getting good coverage and getting like resilience with respect to downward fluctuations. So what we did to kind of find a good idea of how to approximate the reason the upper limit was to run lots of Monte Carlos for like benchmark models that I will show in a second, and just applied coverage correction. So yeah, so we calculate coverage corrected upper limits and found that with a simple expression that you see on the bottom of the slide, we get a pretty good description of limits all the way from the Poissonian regime to the Gaussian regime, although there are some important deviations that I will mention in a second. So first, just the limits that we obtain using this tool as function of the exposure have exactly the behavior that you expect. So there's a signal limited and background limited and systematic limited regime that increases the exposure. The limits are just, and the same is true for the discovery reach. So one just obtains what one expects. It's easy to calculate by just specifying like the signal shape and the statistical significance of the discovery and alpha is alpha. Okay, but what's interesting is that this actually agrees very well with Monte Carlo results, things that we obtain. So these are just 5 models that we used in a paper a couple of months ago where we tested this. Just a 1-bin model and a 2-bin model, and then models with different shapes. And this is just 1D, but this generalizes to arbitrary dimensions because it doesn't matter which order you put bins together in the end. So basically we just checked then with Monte Carlo how well the field produces discovery reaches, and this just works very well, as you can see. So there are 10% differences maybe, not more. And then for the upper limits, this was substantially more work because we had to do the coverage correction. You see for the 5 models on the plot on the upper left that this equivalent counts method gives good results if you calculate 95% confidence upper limits. So typically this agrees well. Sometimes there are deviations up to 30% or so, but usually this agrees very well with what you get from coverage corrected maximum likelihood ratio. And to understand this, the biggest deviation actually you see for model 2, which if I go back 2 slides, you see is kind of a 2-bin model. There's 1 bin to the left with very low signal. No, sorry, very low back. So the signal is the red line that's flat. There's a region where the background is extremely small, and then there's a region where the background is very large. So that's like a 2-bin problem with very large differences in the background. And this is the case where we saw the biggest deviations. Now for the 1-bin model 1, you see that the red line, which is this equivalent counts method, agrees very well with the Monte Carlo results, which have these steps, which just come from the Poisson nature of the problem. For model 2, there is this, there you see if one increases the background, that there is first a flat region, which corresponds to negligible background, and then there is a plateau, which corresponds to negligible background in just one of the 2 bins, and then this starts to go up, which corresponds simply to the background limited regime. And you see that in this plateau there are large deviations actually from our method, and we could trace this back to kind of a level splitting phenomena. If you plot the maximum likelihood ratio, then this has for the Monte Carlo results, this has a like band structure or level structure simply because of the Poisson nature of the problem. And then in the case where one bin is completely in the Poisson limit and has this level splitting and the other not, then what happens is that the levels basically split, and the way you calculate upper limits, how to say, basically the threshold that you get when doing the coverage correction becomes different from what you would get for a pure Poissonian process. So that's, I think, the largest deviation that we get, but that's maybe a special case. Then, if you look at...
I don't want to interrupt. I just want to keep track of the time. Since we have the two different talks, we're closing in on a half an hour. This is all super useful, but
yes.
Just okay.
No. I'm also having the time here, so I try to wrap up now, more or less, or go through the rest a bit quicker. So then there is signal discrimination that we can do. So basically looking at profile likelihood ratios. And basically you can do this in two ways. One is to look at the Fisher information geometry and then calculating geodesic distances, and then by something that we call the equivalent shape method, then the confidence contours based on geodesic distance are easy to calculate. So as soon as one, and these methods actually take as functions signals with functional dependence, so with dependence on model parameters. And what one can do is simply calculate based on the Fisher information geometry the confidence contours, as you can see, but also the streamline visualization of the Fisher matrix. So basically the boxes that you see there correspond to 1 sigma regions, and the distance between lines to 1 sigma distances. So that's a more general visualization than the confidence contours that you get. But basically they are the same as the confidence contours. Now this doesn't work for scenarios where things are non-local. So if you have multiple parts of the parameter space where you get similar signals, and in these for these we also developed an approximation scheme which basically maps the complicated signal plus correlated background on uncorrelated signal and uncorrelated background noise, as shown on the bottom of the page. The main advantage of this is that one can now do this for millions or billions of points and calculate for all the points the equivalent signals and equivalent noise, and then just run a clustering algorithm through this and see what regions of like your favorite MSSM SUSY parameter space are observationally equivalent and give the same signal and whatnot. And this works also well. So basically we get good agreement between MINOS from MINOID and the equivalent shape method and Fisher information metric as shown here. And then just one word about Fisher information flux, and then I'm done. So basically, if we talk about signals, we are interested in one. The Fisher information corresponds to 1 over the variance, so 1 over sigma squared. And what this framework allows us is to then take the derivative with respect to exposure, but like on a bin-by-bin basis. So you can then easily see how much improving the exposure in a certain bin will improve your sensitivity. If shot noise dominates, this is just the signal-to-noise ratio, nothing surprising, but this also works for arbitrary background uncertainties. And this is like how the Fisher information flux looks as for the model that I was showing. So in the limit where the exposure is very small, this just agrees, so the green dotted line agrees very well with the signal-to-noise ratio. Naive signal-to-noise ratio, but if it increases the exposure, actually the information flux drops and drops and drops. And you see that the sidebands become increasingly important, which is not a surprise because you need the sidebands to constrain what's your background in the signal region. And that's easy to calculate also. As you see, it's just like calling one function, and then you have the information flux, and you can also do it more fancy for sky maps. I don't have time to talk about this, but the point is that's complete quantitative. So if you integrate then the Fisher information flux over time, and over like the different bins, then you basically get back exactly the variance that you would have obtained if you would have started with the full expression in the first place. So it's especially useful for astronomy considerations where one has different complicated backgrounds in different sky regions and has to make choices about where to look. Okay, there are lots of things we want to look at in the future, especially related to dark matter searches and also to MSSM scans. In particular, I think it's very interesting to think about systematically the model discrimination power of experiments for very large parameter spaces in the MSSM. And this is something we want to do in Gambit. And yeah, these are my conclusions. So Poisson likelihood problems are omnipresent, and yeah, we hope that with Swordfish we can have a nice tool, or we'll have a nice tool that will at least make our life easier to think about where to look in astronomical observations for dark matter or how to optimize direct detection experiments. And yeah, we introduced a bunch of approximation schemes and visualization techniques that should make the work with this kind of problems easier in the future. Yeah, that's it.
Great, thank you. Can I ask a quick question? When you had, I guess, going back to around, slide 17 or something, when you're doing the contours where the signal depends on some parameters, some theory parameters.
Yes.
You need to know derivatives. So are you doing those derivatives just? Again, you're giving it discrete values of S, and you do like finite differences, or how is that working?
Yeah, this is fine. So this is just right now. This works like you provide an arbitrary function of two parameters, which maps onto array, and then it does internal different numerical differentiation.
Okay. Have you thought at all about trying, if you can provide that function, being able to, do like autodiff or something to get those the derivatives?
Sorry, I didn't understand. You are interrupted.
All right. Have you thought at all about if you could provide that function getting the derivatives through something like automatic differentiation or something like that?
I think this would be pretty cool. I haven't looked into this. The point is that this right now anyway only applies to two-dimensional parameter spaces. So okay, that's not a showstopper. I think it would be interesting to have analytic difference. Yes. Yeah.
Okay. So I didn't realize that. So right now, you can't extend to beyond two parameters for the signal can only depend on two parameters.
Yes. The point is a bit that for this two-dimensional visualization, what happens is that if you have a higher function with more parameters than in the other directions, it doesn't use the geodesic equation, but it would basically assume that everything is Gaussian and get rid of these parameters by profiling them out. Basically, that's a matrix inversion. So the point why we didn't go further there is that in reality, if one throws this, for instance, at MSSM parameter space, 19 parameters or whatever, then you have tons of degenerate regions where anyway this breaks down because the Fisher matrix becomes singular, and there are regions which are identical but far away and so on. And so for this, I think this other method, which is basically just looking at individual points and then calculating the distance just based on the shape of these points and not on derivatives, is much more efficient. So, and then one doesn't need any derivatives whatsoever. The idea is here kind of doing Fisher forecasting in the observable space and not in the parameter space of the model.
Okay. Well, I think that seems reasonable maybe for the MSSM, but there are lots of problems that we have where we expect to be close to, like for the LHC, for instance, we expect to be close to the standard model, and but there's maybe 5 or 6 parameters that we would like to measure, and we know maybe the functional dependence on them. So it would be nice if somehow, I know you can't make the plots nicely, but it'd be nice if it could still somehow do the forecasting.
Yeah, it would be interesting to understand what specific examples you have in mind and what approximations there actually would work and which ones wouldn't.
Okay, great. Any other questions? Okay, well, yeah, so it's impressive work, and we talked a little bit about once this is released or whenever is the right time that we might make some reference to it off of the Diana page. I think this could definitely be useful also, for instance, people that are doing, forecasts of future colliders and things like that. So, great. Okay, thank you.
Okay.
Thank you very much. Maybe we pass over to Jim to introduce the next talk.
Well, not actually me, but Wes. I think he just reconnected.
Yeah, I'm on the line, if you can hear
Great.
me.
Yes. Oh, right. So since you're on the phone bridge, you can't display the slides. Let me see if I can do that.
I lost internet in the last 15 minutes. So.
Yeah, let me try to do that. Okay.
Hi, Wes. Are you at 2 Sigma in New York?
Yes.
Okay. Maybe I met you. Did we talk recently? This is Kyle Cranmer. I gave a talk at 2 Sigma recently.
I can't remember. What's your name? I can't remember.
Oh, Kyle Cranmer. I was talking about some machine learning things. And anyways, hi.
Oh, yeah. Yeah, I don't think I was there, unfortunately. Yeah.
Okay. If you're ready, I have my fingers on the arrow keys, and just tell me what slide number.
Okay. Okay. Sure. Yeah. I mean, I have some slides. Nothing too formal, but I just wanted to tell you about the Arrow project and maybe see how it's related to different systems, data systems problems that you're dealing with, and see if there's potentially some points of collaboration or growth of the project that might be valuable kind of working into the future. So let's go to slide 3. I'll tell you about my background and how I got involved in all of this. I do live in New York. I'm employed at 2 Sigma Investments. One of the reasons that I'm at 2 Sigma, they're an investment manager, primarily an investment manager. They operate a number of hedge funds and different lines of business, but they are 2 Sigma is a big consumer of data science tools and machine learning applications. And so I have been looking to work to get myself into a situation where I can work directly with the users of things like the Python kind of machine learning data science stack, where I can kind of work to innovate and grow the open source data science ecosystem. I got started in this business about 10 years ago. I got interested in the Python language at the end of 2007. Started what became the Pandas project, and I've spent the last 6 or 7 years working, kind of advocating for the needs of everyday data scientists, people who are doing data access, data cleaning, feature engineering, machine learning, data visualization, and thinking about the systems problems that affect the quality and the ability for normal people to do data science work. So kind of solving systems problems as well as user interface and tool accessibility problems. In the last few years, I've gotten more involved in the Apache Software Foundation and big data projects. One of the major artifacts which has come out of my sort of struggles with systems issues, kind of in the low-level internals of data science projects like Pandas, is the Apache Arrow project, which is what this presentation is about. And I've worked on many other open source projects over the years. But at a high level, the motivation for all of this is that if you think about libraries like Pandas and R and kind of what everyday data scientists or data scientists are using every day for doing data wrangling and machine learning. All of that was built on a foundation of technology tools, which hasn't really changed all that much since the 1990s. So if you think about, what is NumPy, for Python, we're not that far from being effectively interpreted Fortran 90. So it's a very primitive computation model that's oriented around homogeneous blocks of tensor data. It doesn't work very well with non-numeric data, and in the analytics and data science world, there's a lot of string and categorical and non-numeric data that has to be worked with. The run times for executing operations in memory are not very intelligent. Like, operations are mostly eagerly evaluated. There's no query planner. There's no multi-core schedulers. So it's all, a lot of what people are doing is single-threaded, eagerly evaluated, kind of in the Python interpreter, and so it's not very efficient. So over the years, a lot of pain points have accumulated dealing with much larger data sets. I think that my advice for data scientists is that they should plan to have about 10 times as much RAM as they have data, which is a bit shocking to people when you have a machine with a terabyte of RAM that using the normal data science tools that doesn't work very well on 50 or 100 gigabytes of data. Even adding RAM won't solve the problem. So there's a lot of infrastructure problems there that need to get dealt with. So when we go to slide 4, at a high level, I think one meta trend is that RAM, the performance of RAM and the performance of disk is converging, and so one thing that we need to plan for and build into our in-memory data infrastructure is to be able to work with data on disk as though it were in memory. So to be very friendly to memory maps and shared memory. And people have been working with large data sets on disk in scientific data formats like HDF5 and just plain memory mapped files with a little bit of metadata to describe tensors. But when you start going beyond simple tensor, multi-dimensional array data and dealing with very large tabular heterogeneous data sets, how to work with those data sets with zero copy out of shared memory or memory maps at arbitrary scale becomes a lot more complicated. And the tools that like the infrastructure that a lot of modern data science tools are built on aren't designed for that use case. And so particularly with what's happening with hardware, this is becoming increasingly important. Go to slide 5. Another trend is that the machine learning and quote-unquote AI stack is evolving quite rapidly, and particularly with the growth of the open source software stack, that the solutions that people are building to solve production machine learning pipelines are involving many different components. So you might have a streaming data collector that is doing kind of data, real-time data collection and streaming ETL. You have some systems which are responsible for data preparation and feature engineering. You fit or update machine learning models, and then you serve model scores to production from those models. And so one of the problems there is in building these architectures composed of many different open source components. One of the big pain points is how you plug the systems together at the data level. And so there's been a proliferation of different serialization formats and data ways of moving around data, which have different levels of efficiency. And if you're working with large amounts of data, all of this conversion costs of plugging systems together, which use different internal data formats, can be 80 or 90% of the runtime of a particular application is just spent converting data from one format to another. I'll go to slide 6. And so so my thesis in all of this is that we should be designing our in-memory data management and data process and kind of runtime data processing tools around the presumption of being able to interact with data on disk with zero copy. This also helps with inside runtimes, the ability to spill large data sets or fragments of computation to disk at very low cost. It makes things a lot more flexible when you're building a data processing engine. Another benefit of being able to do zero copy is that two systems can work with the same data set without necessarily occupying a huge amount of RAM or producing multiple copies of that data set in RAM in different process address spaces. Go to slide 7. So I'd been grappling with these problems for several years by the beginning of 2015, and I spent the majority of 2015 basically surveying the big data ecosystem and the data science ecosystem, and looking at, trying to figure out if other people had experienced these problems of, efficient data interchange between systems and, an efficient in-memory representation for analytical data processing. And it turned out that there were a lot of people that had stumbled on this problem space of being able to move data efficiently between systems, and to move data in a format that is efficient for analytical processing, so the kinds of things that you do in feature engineering or machine learning. So by the end of 2015, we had assembled a large collection of open source projects to say, let's build a solution which we can drive as an open source community standard for representing data that can be zero copy shared through shared memory, and that is suitable as a primary runtime format for in-memory data processing. And so now, 2 years later, the way the project has grown is into what I'm describing now as a cross-language platform for developing applications that process data in memory. One of the primary things that we've worked on specifying and kind of where we spent a lot of our time is designing a memory format for tabular data sets, which are, I think in my experience, the most complicated things to work with. So in the data science world, these are thought of as data frames. In the SQL kind of analytic database world, they're just thought of as data sets or tables. That it's column-oriented, which means good data locality for analytical query processing, and the data format is designed so that it can be used in a shared memory map setting. So whether you have a gigabyte of data or a terabyte of data, you can interact with it at effectively zero overhead, subject to the performance of the underlying operating system, I/O, and so forth. We've been building reference implementations of the project primarily in C++. I've been leading the development of the C++ implementation. There's also a Java implementation, and we have compatibility tests which produce data in both implementations and send them back and forth. A number of people have asked, if we could just have a single implementation in C++ and wrap it in JNI for Java. And we certainly could, but there's some there's some key players in the project who wish to have everything natively implemented in Java. So I think we'll eventually see JNI bindings for the C++ libraries as well. There are C bindings for the C++ library, which have been built by some members of the Ruby community. So we have Ruby bindings via C to the C++ library. Python bindings and interoperability with NumPy and Pandas in the Python ecosystem are going directly through the C++ API. And we also have a JavaScript native JavaScript implementation that's in active development right now, with the intent there that you could stream data from any of the other implementations to the browser or to to JavaScript applications. We'll go to slide 8. So at a high level, the key parts of the project are the memory format, which is optimized for modern hardware. It's not just being used on CPUs. We also have a group of users which are being led by NVIDIA and MapD and a few other startups who are doing using Arrow on the GPU. So they're using CUDA IPC to share memory between different applications to leave data in place on the GPU and use Arrow for the runtime data format. So having both an efficient runtime data format and the zero copy IPC makes building these heterogeneous applications much simpler. We've spent a lot of time on the schema metadata, so the ability to represent all of the different varieties of data that occur in the wild, from primitive numeric types and strings to more complicated structs, variable length collections and unions. So effectively, the goal is to be able to ingest quite messy data to Arrow format. You could have you could ingest JSON data where different fields have different types, and there's suitable metadata to describe a field which may be one of any collection of data types. Go to slide 9. Let's see here. Let me skip slide 9. Let's go to slide 10. So I'm running low on time here. So one of the big challenges in a project like this is effectively the chicken and egg problem, where different systems have different runtime data formats that they are already using internally. And so just from the perspective of data interchange, Arrow makes things architecturally a lot simpler by having a single data format which can be handed off from one system to another. The goal in the long run is to have more systems using Arrow as their native runtime data format, so the cost of sending data to another application there is no conversion costs at all. And so if you were a Pandas user right now and you wanted to interact with a system that uses Arrow, you would need to convert from Arrow memory to Pandas's native internal format. But our goal with the Pandas project and Python in particular, on a sort of 2 to 3 year horizon, is to move the internals of Pandas to using Arrow natively internally. Go to slide 11. So one project where we've been collaborating and have had a lot of success is the Ray project, which is a machine learning framework being built at the Berkeley RISE lab. And so a software component that they developed and contributed to the Arrow project is called Plasma, which is a shared memory object store which brokers manages the lifetime of POSIX shared memory across a pool of processes. So you might have one process which would allocate a page of shared memory, write a bunch of tensor data to it, and then that data is made available to other processes. But as soon as no processes have any further references to a particular object, that memory can be evicted and freed for other for new memory. And so this is all sort of all part of the Arrow C++ libraries. Go to slide 12. So we've been focused on 2 types of data structures in the so far, and this is certainly not an exclusive list. And I think over time we'll add more types of different varieties of data based on the same kind of I/O and data management stack internally. But a lot of the project is oriented around the columnar table format, which is a collection of heterogeneously typed array objects. But we also support traditional multidimensional tensor objects. And so what we're seeing in some applications is using a heterogeneous table to encode the structure of a much more complicated data set, which contains collections of tensors and other objects. And so there's one table which describes the entire data set, kind of its hierarchy and structure, and then the individual components, essentially subtables and other tensors, are then written out in separate memory regions. And so all of that is then deserialized in applications with zero copy as a collection of objects stored in shared memory. Slide 13. So I'll spend a few minutes just talking about the, since I understand that CERN and you all have a lot of C++ programmers, so give you an idea of how we've been thinking about building primitive memory management and data management tools for C++ programmers. So I've been leading the development of the C++ library. It's designed to be easy to use. It is very conservative in its use of C++ features. So it uses Google style. It does not throw exceptions. It uses very limited, in the public API there is limited templates and limited, a lot of the code is compiled and not in headers. But so there's a memory management and I/O sort of subsystem which handles hierarchical memory references, memory maps, shared memory, and so forth. Type metadata for describing data types and schemas for tables and arrays. There's data structures for arrays, tables which are collections of arrays, chunked tables, and there's also a tensor type for dealing with tensors in the same, or multidimensional arrays in the same memory model. And the last part of this is the messaging layer, which deals with the mechanics of serializing metadata and reading and writing data to different virtual address spaces with zero copy. Let's go to slide 14. So a couple of primitive memory management tools at the center of all of the data structures is the buffer object, which is an abstract type in C++, which manages effectively a block of memory. And so there's many different types of buffer implementations. So there's a buffer for normal heap allocations, which come from malloc or POSIX memline. There's one for memory mapped buffers. We're planning to add one for POSIX shared memory. And so it's a simple interface to implement. So if you have a particular kind of allocation strategy or memory lifetime strategy, the goal is to model that with the buffer concept and the memory pool, which is essentially an allocator interface for keeping track of buffer allocations and enforcing. Memory pools can also be used for enforcing memory limits and keeping track of how much memory is allocated in certain regions of computation. And so if you've looked at the internals of an analytic database, this is all quite standard stuff that's used in database runtimes, essentially creating arenas and pooling memory to prevent kind of runaway memory use in different threads of computation. Slide 15. So the key data types for schemas are the base data type, a field, which is a names type, and a schema is a collection of fields. And so a schema would describe all of the columns of a table in Arrow. Slide 16. So the primary data containers for columnar data are the array object, which is a fixed size statically typed statically typed array object. So whether for any of the supported types in the project. So if you have a data set that is streaming or composed of multiple regions of data, these arrays can be composed into a chunked array object. So it might be that you have, a collection of arrays which are all semantically part of the same data set. And so we've been designing for kind of this streaming or chunked data use case in mind, so that you do not have to have all of the data in a data set in a single contiguous memory space, which has been a limitation in some traditional scientific computing tools. The record batch is a primitive, is a table, each of whose columns is a contiguous array object. And there's a table object, which is it can have, each of the columns can be chunked. So they might have one chunk of data, or they might have multiple chunks. So slide 17. I guess I can skip over this. So there's I/O interfaces, the kind of abstract interfaces we're dealing with for dealing with I/O to different sinks and sources that understand Arrow's kind of memory management, sort of memory lifetime machinery. And then slide 18. So we're dealing with reading and writing data. We serialize the metadata using, we have schema files that use flat buffers. We could use protocol buffers or thrift or something else, but we decided to use flat buffers so that interacting with large metadata will be pretty cheap, and a tool like flat buffers is good for that. But these messaging tools are designed for streaming large collections of tables as a sequence of messages. And so when you send or write a message, it has a small metadata prefix which describes the payload of data. And when you read it back, you parse the metadata, which is a small metadata, and then you construct buffers which reference the underlying message body. And if that's coming from a memory map or shared memory, then that will be 0 copy. But if you read from some other source which needs to allocate memory, then the I/O interface would allocate memory. Slide 19. So we do have a tensor type which is designed for interoperability with traditional scientific computing and array processing frameworks, so things like NumPy and TensorFlow. And the idea is that the internal data buffer its memory lifetime is tracked by an Arrow buffer instance, and then we apply a type and shape and strides to deal with the shape of the tensor and the memory order. And so this is being used quite heavily in things like the Ray project for machine learning in a multi-process setting. Slide 20, and then I realize we're running out of time, so I don't know if we'll have time for questions. But so my medium-term plan and where I'm focusing my work in working on the Arrow project is to rebuild a better foundation for projects like Pandas, which is an in-memory data frame processing tool for Python programmers. And the objective is to have native analytics which run on top of Arrow memory. So that would enable executing analytics directly on data that is on disk or in memory. To have a query planner which is able to use look at the system where it's running and decide which versions of operators to use. So using SIMD accelerated versions, we'd be able to choose GPU-based kernel implementations if there's GPUs available on the system, but generally with the objective of maximizing how much we're able to utilize the hardware that is available. Whereas the current runtime in a project like Pandas is very primitive, very single-threaded, and does not feature these kinds of cross-operator optimizations, multi-core scheduling, or hardware accelerations. This will also be benefited by more efficient I/O and streaming data access, particularly from things like Parquet files, which have become kind of a standard data format for analytical data sets, and just generally being a lot more efficient and careful about memory allocation and I/O in the runtime. So, so that's a lot of information, but I think the project is on a solid trajectory, and we've grown the contributor base across many different ecosystems and use cases over the last 2 years. We've reached almost 100 contributors on the Apache project, and we're actively looking to grow and accommodate different types of use cases. So I think that for C++ or any native code applications which want to build an efficient port or data interoperability layer with other ecosystems, I think that particularly with the efficiency that comes from the zero copy technology, that Arrow is a strong contender to be the standard tool for that purpose in the future. And over the next 5 to 10 years, I expect that we'll see when new data processing engines are built, that rather than design their own proprietary incompatible runtime data formats, that they will choose to use Arrow as their runtime format, and that will bring new levels of performance and interoperability between systems. So I'm optimistic, obviously, because I work on the project, but I think in general, to make systems more compatible and more efficient, will be very valuable over the next decade.
Okay. Any questions from the room?
Do you think that Arrow can obsolete Parquet as a format to persistify data, or you still see room for both of them?
Arrow is a runtime in-memory data format, so it's a companion technology to Parquet, whereas Parquet is for serialization and storage. So Arrow is not for storage.
Anybody else? Somebody on video? Okay.
Sorry, this is Kyle. I'm curious. I'm probably not going to formulate my question well, but maybe Jim, you can help. But in terms of when we looked at the different formats that are going on. And in high energy physics, we have these kind of ragged array type structures. I'm curious where the length of the number of entries is varying from entry to entry. I'm curious how Arrow deals with that. But maybe Jim, you can reformulate my question.
Yeah. So we support ragged arrays and variable length collections. The way that it deals with that is using an offsets array, which encodes the position, both position and size. So if you had an array where the first element has 3 entries and the next element has 4 entries, the first 3 offsets would be 0, 3, 7. And so essentially the whole thing is set up so that random access is constant time. So if you have a variable length or ragged collection, you can always access any element in the collection in constant time. But the actual data, the inner data that is in the kind of the child, kind of essentially the elements of the data structure are contiguous. So even if you have let's say a collection of entries that are different lengths, the data inside those entries is laid out end to end in memory. So if you are performing a scan operation, you have guarantee of good data locality.
Great, thank you.
And I can chime in and add to that it's rather similar to the way that Roots baskets work, where the baskets has an offset array at the end of each basket. It's the same as that up to an affine transformation.
Great, thank you. Also, another question that's a bit vaguely stated, but on slide 7, you just talk about, Arrow when it started is sort of trying to define standards for in-memory analytical data processing. Can you just say a little bit, you talked in terms of what the standards themselves look like, kind of what the scope or like how the scopes of the standards versus the actual implementations, like which things are being specified in the standards?
Yeah. So the things that are the main things that are being specified is the columnar data format for tables and structured data. So there's a set of metadata files, which are essentially the binary format for metadata, and there's specification for the memory layout. So like how to deal with essentially how things are cache aligned and padded, how variable length collections are represented, what are the nested types that are supported, so structures, lists, and unions. But I think the biggest thing is the metadata and the descriptions of the logical data types. So that also includes things like timestamps and date and time values. But the actual implementation, like some of the things I described, that are C++ specific are not part of the specification. That are strictly, programming conveniences for C++ programmers, and they're not part of the specification.
Great, thank you.
Any other questions?
I have a little question. This is Wahid. Is it like to get the most out of this? You really still need to have quite a lot of memory, right? Because otherwise you still need to serialize to disk, or is that not right? Or some byte addressable like DD crosspoint or something, but.
Yeah, well, I mean, I think if you have a system that uses Arrow as its runtime memory format for analytics, so you would reap, so by using so you reap efficiency at any level. I mean, obviously, if you're dealing with 100 gigabytes of data, the amount of performance savings, like absolute performance savings, will be much greater than working with a megabyte or a gigabyte of data. But the fact that the read overhead basically goes, there's no deserialization overhead when you interact with Arrow data sets. I think would benefit right? Applications that. Yeah. I mean, but you might. I mean, yeah. If you have even small amounts of data on disk, like there's still, it's still a meaningful performance benefit to not have to deserialize data. But the benefits certainly are more pronounced at scale.
But wouldn't you, once you using more data than you have memory, you would still need to serialize the disk, no? Or do I misunderstand that?
I mean, it's like define serialize. So you can write the data, you can write the bytes from RAM to disk, but then you can memory map the data on disk. Right. And then you use it as though it were in memory, and so you don't need to separately load the data back into RAM. Is the point? So right now, I think with a lot of with serialization formats, traditionally it's like the data is either all on disk or it's all in memory, and so you can write the data out, but then you have to load the data back in. So here there is no dichotomy like that. So you can interact with data on disk as though it were in memory.
Okay, and if one wanted to write different, well, I'm sure Jim's thought about this. For example, interacting with root here to allow, for example, root to Parquet, very efficient conversion, I guess. Is it easy to write? I mean, I haven't looked into it at all, but
I don't know much. Yeah, that'd probably be a question for Jim.
Yes, actually, I have been looking a lot at root to Arrow conversion, which is actually easier than root to Parquet conversion, given the similarity of roots basket offsets to arrows offset. So actually, yeah, I've been developing code that on the fly transforms roots to the same kind of layout as arrow, but not actually using the arrow tools yet. But yeah, that's in the works.
Cool.
Mm-hmm. Yeah, we can even benefit from memory mapping with the roots data too. I've been experimenting on that, and then just cast that cast that basket data as the array if it happens to be uncompressed. That's actually an important point if we're talking about memory mapping, that it doesn't work if the data is compressed. So
right.
Something to think about.
Right. Yeah, I mean, one thing we've been discussing a little bit on the around compression is essentially having compressed buffers, and so it might be that when you access, I mean, we would obviously need to develop some APIs to make this a little bit like have a sane programming model for dealing with this. But when you actually access a particular memory buffer, at that point it is decompressed with LZ4 or Z standard or whatever compressor you're using.
Yes, and that would make the interactivity between root and arrow more difficult, but of course there's something to be gained there. Any other questions? So, not who's leading this meeting?
That would be you, Jim.
Is it really? Oh, okay. Well, if there are no other questions, then maybe we can adjourn.
Great. Thank you to both our speakers.
Yeah, thank you.
Right. Thank you.
Bye.
Bye-bye.
Bye.